So I will show you the actual number example. So this is the X is the characteristic of the patient's age, gender. So it's a 45 years old, female, and she doesn't do any regular exercise, and then she do the treatment A. I don't know, maybe different drug. Uh, treatment is A or B. So it's a 45 years old, female, and then do the regular exercise, and then we calculated all the glucose level calculation. However, actually, we don't have this data. What would be if we give this patient, the first patient, 45 years old female who don't do the exercise, we give her the treatment A, and her result is a 6. But what would happen if we provide treatment B to this person? What would be the glucose level? I don't know, because we don't have this data. And this second patient got a treatment B, so I know what is the result here. But what would happen if we provide treatment A to this second patient? I don't know. So all the case, this is the fundamental problem. We don't have all the data. So if we know all of this data, yeah, we can calculate the average over here, and then you can compare, and you can talk about what is different. However, since we don't have those empty part, the question mark part, so why don't we just calculate the average of 6.5889, and here we are calculating average of these four numbers. So if you calculate the average of these four numbers, then average is 7.125, right? So this is I collected only the t equals 1, so we don't have data here. So I collected only four numbers and calculated 7.125, and then also I calculated all these four number calculation of the average. I got a 7.875. So if you calculate the expected value y given that treatment was 1 minus expected y given treatment is 0, this is minus 0.75. Again, this has a causal plus compounding. So I don't know. Actually, it has a effect, negative effect. So now, what if somehow we can find out the count factor? Count factor is we don't know, but let's say somehow I figured it out. We didn't give the first patient to the treatment B. We apply the treatment A, so we measure, so we observe the data. But what if somehow we can figure it out what number it would have, right? And the same thing, what if I can figure it out somehow? Yeah, I'm not talking about, but we will talk about how we're gonna figure it out. But somehow I can find out. Somehow I can find out the count factor, all of the count factor. Then what you can do is you can simply calculate the average all of this number and average of all of this number, and we can calculate it. So now if you calculate all the number, average will be 8. This is average 8, and this is average 7. So if you just calculate it, the difference will be positive 1. This is a totally different result compared to the previous one. This one has a minus. So actually the glucose level higher, the worse. So which means if you calculate this way, it seems like treatment B, which is t equals 0, has a higher glucose level. So maybe if you are using this number, then we can say A is better. Right? Because the A has a lower glucose level. But if you look at this, A provides a high glucose level and B has a lower. So actually this conclude B is better. Right? So we cannot use this calculation. This calculation means I just collected the data that has a t equals 1. And you just collected the data t equals 0, and you calculate the average and then calculate difference. That is not the actual real treatment effect of treatment A. This is not right one. This is right one. The problem is, how can I get this count factor? So this is the two common, I will talk about two common methods. Actually, there is more, but two common methods of the causal inference. But both of them trying to show you how can I find out, actually it's just estimate. So we cannot say that's the exact number because we never know until we actually try. But we already lose a chance. However, if we can estimate and then using that the count factor, yeah, we can calculate the average treatment effect easily. So actually this the slide and the example is a highly I just borrowed from this open course machine learning for the healthcare. This is about the machine learning course, but there is a causal inference part of the lecture there. First one is the covariate adjustment. Covariate adjustment is covariate is the predictor or the independent variable. That's what another name is a covariate adjustment. The problem is solved only if we can predict the count factor. So how can I predict the count factor? You can use a regression or any machine learning method using the data we collect, and we create the prediction model. Okay, it doesn't matter what is a regression or any machine learning method. We create the prediction model, and using that model, we calculate the count factor. So this model will be the two different models. So what will happen if age is 45, is a male, and then do the exercise or not? And then if we give a B, what will be the result? So we can do a lot of different things, and using those technique, and we can make a prediction model, and using that prediction model, we estimate what would be the result of the count factor. And this method is also called the response surface modeling. So let's take a look at it. This is the real curve. Okay, this is a real curve. This is a real. However, you got a point. As you can see, you got a more point this side. You got a more blue point, but the other side you got a more red. Right. So if we actually this is the x about the individual characteristic. We have to know this is the I think a red one is the t equals 1 and this is a t equals 0, and we don't give a treatment, but what if what would be the result if we give a treatment this person? So this person may have a different number, showing different number here, right? So we created all the count factor using the regression model. Or if we treat t equals 1 here, But what would be if we give a treatment 0 here, right? So we are trying to figure it out, those point using the prediction model. So we can create a lot of different count factor, estimated count factor, and then assuming that count factor is real, and then you can just simply calculate the individual difference and then calculate the average. Then you can get a average treatment effect. However, when this covariance adjustment goes wrong, but as you can see, the red one is always higher than the blue one. But when we don't have actually I took it out some data point here. So if you just take a look at only the red part, what would be the best estimation? This is the linear, right? So if you're using the prediction of regression here, all this count factor will point here. This is totally wrong. Everything should be greater than the blue one, but using this prediction model, every count factor of the blue point will locate here. And you can say the blue one is always greater than the red one. Same thing, if you take a look at the blue, right? Blue is located only here, so this linear model will be pretty good fit here. And if you're using, the count factor will be show up here if we use this as a prediction, right? In either case, we can tell blue has a higher value than the red everywhere. But actually, in the real relationship, is as you can see, the red shows a higher value than the blue value everywhere. So you end up with a totally opposite conclusion, right? So it's possible. So when the covariance adjustment goes wrong, when we don't have a lot of overlap. So actually this is the extreme case. Blue and red doesn't have any overlap. Here everything is blue, and the other side is everything is just red dot. There's no overlap at all. If there's no overlap or just a little bit of overlap, this method, covariate adjustment, will lead you to the wrong conclusion. So you have to be careful. Okay. So if we use a linear model, covariate adjustment with a linear model, so linear model will be just like this. Here the x can be a vector, but we can just use a single number because we are using the age as the attribute of the patient, but actually we can have a way more. So x can be a vector and beta can be a vector, but in this example, it's not a vector. But you can expand this one as a multiple case. So if this is a linear model, this error, expected error should be 0, right? So we already take a look at it, this one. And then t is the treatment 0 or 1, right? And if you just calculate the individual treatment, so it will be this case, this is a t equals 1. So t equals 1, so I should write it, this one is 1. And then this one, this gamma times 0 is gone. Because it's times 0, this is gone. So what we'll have is the beta x plus gamma plus error 1 minus beta x plus minus error 0. But this one and this one will be cancel out each other, only the gamma left over. But what happened to this one? Because the expected value of this error is always 0, there's an expectation outside, so they are gone. So only thing left over is the the gamma. So if you just gamma is the deterministic number, so if you just apply another the expectation over the patient or the data, individual data, your ATE will be the gamma. So in that case, you can just find the here what is y equals beta x plus gamma t, and you do the regression, right? And you can find out the gamma, and gamma will be the average treatment effect. So here, for causal inference, we have to estimate this gamma accurately. Gamma is my interest here, not y. Previously, I focused on the how can I create the model that can predict y more accurately, but actually this case, this is not true. I wanna estimate gamma more accurately, not the y. Non-linear model case, still the calculation will be the gamma, because this will be the beta x plus gamma when t equals 1, gamma times 1, plus the delta times x squared, right, minus beta x plus gamma times 0 plus delta x 0. So this will be cancelled out, and this will be the cancel out, and this is already multiplied by 0, and this is just gamma. So only gamma left over. Of course, there is an error term both sides, but error term, expected value of the error term is 0, so you have only the gamma. However, if we use, so this is the case, a real relationship has this nonlinear term, but if we use just a linear term, what will happen is the estimated gamma is the real gamma plus this part. So depends on this delta, or depends on these things. Your estimated gamma can be a lot wrong. It's significantly different. It's possible. So we don't know the real relationship has a nonlinear term or not. But if you just use a linear term, but in fact there is a nonlinear term, your estimated gamma can be a lot wrong.